Okay, all right. Well, for today's lecture, I thought we could do just a couple, I guess, fun things. And so today's content I will not put on the final exam, but this is just kind of like, this is just some neat things or just some fun things that I thought we could do. So anyway, one thing I wanted to show you was to show principal components analysis as a way of kind of uh, as a form of like data compression in terms of, because we can use principal components analysis for dimension reduction. And if you think about what what certain forms of data are, it can be used as a way to kind of reduce the amount of data that we store. And so here I wanted to, I have this image here. This is an image by Ansel Adams, a famous nature photographer. And this image is 899 pixels by 720 pixels. Okay. And what we will do is I'm going to basically where if you think about it, each pixel here, I don't know how to. Okay, it's kind of hard to see, but and when I zoom in here, it gets blurry. But every single pixel is basically a little rectangle with a number inside. And that number is either a high number or a low number. Representing how bright or how dark the that value is. Okay. And so what I want to do is I want to reduce, we can treat this as a big matrix, 899 columns, 720 rows. And what I want to do is I want to try to reduce the matrix. Basically, if I treat each column, as its own variable, can I reduce the number of columns? Can I reduce the number of columns to something less, right? Because if you think about each column, adjacent columns probably have a lot of correlation between them, right? Like if you think of this one column of pixels right here, and then the column of pixels right next to it, there is going to be a lot of high correlation. But of course, they're not exactly the same, and that's why we're able to see the image. So anyway, I'm going to load up this library called Imager, which just allows you to kind of work with images in R. And apparently, I have to get it synced up here. But let me go ahead and load this image into R. Okay, and you can see it's it gets loaded into memory, and the dimensions of this are 899 pixels by 720 pixels. Okay, 899 by 720, and then there's a 1 and a 1. Okay, and this allows there's 3 color channels. It's a black and white image, so we're not using any of the color channels. And then it also allows for, multiple, like if it was a GIF or a movie, you would have multiple kind of frames. And here we're just looking at one frame. So here I'm going to just reduce it down to just a single matrix, 899 by 720. Okay. And so you can see Adams is just a large matrix, and I can do dim of Adams being Ansel Adams, the photographer. And if we just kind of look at maybe the first 5 rows and the first 5 columns. Okay, so this is like the top top left corner right here. Okay. And I can plot the image in R. Let me just kind of make this a little bit bigger. All right. So this is the image being plot, and you know, and if I can also just kind of subset it 1 through 5, 1 through 5, and we would just plot basically this top left corner. Okay. This is the kind of the image being plotted there. Okay. It tries to kind of blur things together. Okay, but anyway, what I'll do is I'm going to go ahead and do principal components analysis. And so in order to do that, what I'm going to do is I'm going to calculate the mean of each column here. Okay, so we're going to treat this as 899 columns in a matrix with 899 columns, and I'm going to go ahead and find the mean of each column. Okay, so Adam means is now, you know, just a vector with 899 values in it. And what I'm going to do now is I'm going to subtract the column mean from every column. And I'm going to now, and that will center the image. Now, if I were to plot this, okay, so I have Adam centered, so I transposed the image, subtracted the column means, and then I transposed it back, which is, you know, kind of a little bit of a trick that you've seen in your homework and stuff. If I plot this, what happens to the image, okay, is we get these kind of these vertical streaks. Okay, so this oops, let me just go ahead and delete that one. So here's the original image, and this is the image after I subtract the column means. Okay, and basically what's happening is if there is a lot of kind of, if you think about one column of pixels, if that column of pixels is, say, quite dark, right, meaning the average value is low, okay, and we subtract those off, okay, because we're trying to center all of these things. The average pixel is going to be kind of low, then that's going to have, when we subtract a small value from it, it's going to kind of comparatively brighten that column. Okay, whereas if there's a lot of kind of brightness in the in that column, so this column of pixels, maybe there's more lighter pixels, and so this column of pixels will have a higher average, and so when it gets when we subtract that, it's going to end up kind of brightening or darkening it. Okay, and so so basically we've subtracted a value from every pixel in the column, and so we're kind of getting these vertical streaks. Okay, this is just to say all we're doing is we're just centering the matrix. Okay, and we can just verify, like, is the means of these columns now 0, and I can just do all equal, and indeed the means of the column means is all equal to a bunch of zeros. Okay, so how do we do principal components analysis? Well, first we're going to find the covariance matrix. So I'm going to take, I've got 899 columns. So my covariance matrix, the dimensions of this covariance matrix is 899 by 899. And I'll go ahead and I'll make my text a little bit larger for you guys. So 899 by 899, this is my covariance matrix. And I'm going to ask R to find the eigenvectors, eigenvalues and eigenvectors of my covariance matrix. I ask covariance for this centered matrix. I'm going to do this, okay? And so if we ask for the structure, just what is this? I have one is the list of eigenvalues, and then the second is all of the eigenvectors, okay? And all of the eigenvectors, there's 899 of them, each of them 899 long, right? So the covariance matrix is 899 by 899, and all the eigenvectors are also going to be 899 by 899. Okay, so what I can do is I can say, all right, well, let's just take some of these eigenvectors. And so arbitrarily, out of 899, I'm going to just say, let's pick 50 of them. Okay, so I'm going to kind of take the first 50 eigenvectors, right? And we can see, all right, I'm going to say this is the first 50 principal components. And so we can see this data, there's 899 rows, 50 columns, okay? And I can project the data onto those 50 principal components. So I'm basically doing a rotation of the data, okay? So I'm going to take atoms centered. So again, if we ask what are the dimensions of atoms centered, there's 700 something pixels, okay? 720 pixels by 899. And we're going to now reduce this by multiplying them together. The dimensions of this thing is now 720 by 50, okay? 720 by 50, okay? So the data is all in here. Now, if I try to plot this, okay? If I try to plot this value, 720 by 50, it is not going to make any sense at all, okay? So if I do atoms underscore projected, okay, it looks like this, all right? So this doesn't make any sense at all. This is 720 pixels, 720 by 50, okay? We have a matrix of 720 by 50. Basically what we've done is the original data is 720 by 899, and we've reduced those 899 columns down into 50, okay? And the 50 columns look like this. But somehow this 50 columns contains pretty much most of the information contained in this image, okay? Which is a strange thing to think about. So what I want to show you is I have all of this stuff in memory, and I'm going to what I'll do is I'll delete I'm going to delete not everything, okay? Let's I can delete the original image and the centered image and the covariance matrix and the eigenvectors. I'm going to delete those, okay? And so I no longer have, all I have in memory here are the vector of means, atoms means, sorry. So I have this vector of means, okay? I have the projected data, okay, which is 720 by 50, and I have the 50 principal components. Okay, so I have this data 899 by 50 pixels, 720 by 50 pixels, or this is 899 by 50. This is kind of my first 50 principal components. This is the reduced data, 720 by 50. And then this is just a vector of means, okay? And so this is the data that I have. And what I'm going to do is, again, I reduced it to just those 50 principal components. And now I'm going to try to recover the original image, okay? So you can imagine kind of compressing the data down into this kind of structure. And you can see how much space and memory does this consume? 350 plus 281 plus 7. We're looking at around, I don't know, 650, something around there, 640, 650 kilobytes, okay? Versus if I do load the original data, okay? The original data is closer to 5 megabytes, okay? But we'll go ahead and again, I'm going to just kind of remove that, all right? But and we'll try to recover something close to the original data. So I'm going to take my projected data and I'm going to undo the rotation, okay? And so, a student asked, like, don't you need to invert the matrix, right? Because the principal components, right? So when we projected the data, I took the centered data and I multiplied it by this matrix. And then the question was, don't I need to invert it? Okay. And the answer is normally yes. Normally you would need to invert the matrix to kind of undo it. But the principal components matrix is what we call a rotation matrix. And so when you invert the rotation matrix, you end up with the transpose, okay? The inverse of a rotation matrix is its transpose, or the transpose is equivalent to the inverse of its inverse of the matrix, okay? So the question is, so we can do file reduction in R using this PCA method? Well, it's not perfect. It's not perfect, but yes, okay? So so I've rotated, I'm going to rotate it back, okay? So I'm going to multiply this by the transpose, which is kind of like inverting the matrix, except, now we have a smaller thing. All right, and so now my reconstructed matrix, okay, now we can see, oh, it's 4.9 megabytes, right? So if you take this 720 by 50, and you kind of reconstruct it, you'll get a matrix that's 720 by 899, okay? And that's going to take up, 4.9 megabytes of memory. And then we're going to add the column means back to it. And let's take a look. Okay, I'm going to go ahead and delete this streaky image. Okay. Okay, so here is, this is the image reconstructed here, okay? So I don't know how it's coming across on Zoom, but it looks like a blurry, kind of a pixelated, low-res version of the original image, okay? So if I load up the original image, okay, so here is the original image. It looks sharp and crisp and beautiful. And here is the image after I reduced it to something much smaller, okay? This is I kept 50 of the principal components, right? So the original image and this is keeping only 50 of the principal components. So, you know, we could, if we wanted to, we could perform image compression this way. All right, this is not how image compression is done on the web or anything like that, where we want to kind of save file space. It's not done this way, but it could be done. Okay, it is a feasible method. Okay, to compress images this way, and again, you know, we went from around 5 megabytes down to around, you know, some less than 700 kilobytes. Okay, and yeah, you know, because you are throwing away data, the image is not as crisp as the original. Okay, and so I wanted to kind of go through and show you like what happens when you keep, say, only one principal component versus 2 or 3 or something like that. And let me see. All right, let's try this. Okay, so I'm gonna take this and just run some of this stuff here. Okay, so I'm gonna go ahead and do this. Let me delete all of these graphs here. I'll take a little moment as it cycles through. So here it's kind of going through different numbers of principal components. And you can see as we keep more and more principal components, the image becomes a little bit more in focus, and you can see a little bit more of the structure of the data in there. Okay, so this is would say 90 principal components, 150. You know, at a certain point, okay, so let me just kind of have all of these images here. So if I go all the way down to, say, so basically for each of these, I did principal components analysis, and for each of these things, I kept only, say, the number one principal component. So if you keep only one principal component, so you take, you know, you have the original image is 720 pixels by 899. We're reducing all 899 values down to 1. Okay, and if you keep only that one value, this is the image that you are able to recreate. This is the kind of the variance that is captured by it, and it's again, you can't recognize any of this. Okay, if you keep 2 principal components, it's still a huge blurry mess. With 3, now we have a little bit of structure. We have a bright spot here and a bright spot here. You still can't, you have no idea what this image is supposed to be with 4 pixels still, or 4 principal components, okay, and 5, and with 6 principal components, it's still very difficult to tell what this is an image of. You know, if you kind of step away and you squint, maybe, okay, you can kind of start to see it a little bit. I would say maybe around, so here I'm keeping more principal components, and now at around 16, it's starting to kind of take shape here. Okay, with 20 principal components, now maybe around 25, we recognize, okay, this looks kind of like a scenic image, river, some mountains and sky. It's you can't make out any detail in the forest. Okay, because if you think about what is principal components doing, right? We have the covariance matrix that tells us how all of these variables relate to one another, and we kind of reduced all of that down to just a few components, and so we're keeping a lot less. We're throwing a lot of that variation information away, right? How many principal components you keep is directly related to how much of the variation in the original data you're able to explain. And so as we keep more principal components, our image increases in detail and contrast. Okay, and so at around 90 principal components, okay, I'd say this is a pretty good representation. Okay, and as I keep more principal components, we're not getting a whole lot more detail, but we are increasing, I would say, in kind of the contrast between the bright and the so this is with 500 principal components, and this is practically the same as the original image. If I plot the original image, so this is the original image. Okay, with 500, and here's the original image, and I would say it's very difficult to tell the difference between the original image, 500 principal components, or even like 400 principal components. Maybe a little bit between 400 and 500. But as I reduce the number of principal components, the picture becomes a little bit more washed out. And then as you reduce it even more, it becomes, kind of more blurry. And the idea of it becoming kind of gaining more contrast and more sharpness reflects kind of the idea of capturing more variation. Because when it comes to an image, if you think about a black and white image, what does it mean for there to be variation? Variation is kind of how far is, the one way to think of variation is how far apart are your highest and your lowest values. And if you think about what do the highest and lowest values in the image represent, they represent kind of your brightest areas in the image versus the darkest areas in an image. And so as you keep more and more principal components, okay, you're going to capture more variation that exists in the original data. And as far as an image goes, capturing more variation means getting more contrast. You are now separating, making a stronger distinction between the highest values and the lowest values, okay? With 70 principal components, the trees out here in this kind of foreground of the forest all just kind of blend together, right? We are not making any kind of distinction. We're saying, the pixels here and the pixels over here, they're all pretty much the same, okay? As we, increase, go to the kind of the original image, all right? Now we're trying to pick out even more variation. And we're saying, oh, you know what? There actually is a difference between some of these dark pixels over here, okay? There's some of these pixels are a little bit darker. They're all kind of dark. This is a dark part of the image, but some of these pixels are a little bit darker than others. And that's because, as far as the picture goes, some of the tree branches just are a tiny bit darker, get a tiny bit more or less sunlight than other images, and they're being reflected in this thing, okay? Whereas, as you reduce the number of kind of values here, okay, they all kind of get blurred together, and we're not really making a distinction between these different images, okay? And that's the kind of the double-edged sword of dimension reduction. We like dimension reduction because it's easier for us to think about, right? When you do dimension reduction, okay, two students who have, if the same GPA, are viewed the same, right? If one student has a 3.8 GPA and another student has a 3.8 GPA, and if we reduce the students down to just one number, it's easier for us to kind of look at that, and these two students, both with the same GPA, are viewed the same way. But the truth is that there are going to be differences, right? And there could be some major differences, especially if you're just going down to one component, okay? But you know, one student could have taken a bunch of easier classes or something, right? Or another student could have had, you know, different different curriculum or something, stuff like that, and that's kind of lost in the image per se, okay? Or in the when you do dimension reduction. But again, it's as far as this goes, you know, looking at this row, one row of pixels and the row immediately below it, they're going to appear very, very pretty much the same, okay? And it's only when you kind of say, you know what, I need to capture more information, more variation, that we're able to start to say, okay, you know what, there is a difference between this row of pixels and the one above it and the one below it, because now we're going to try to capture more information. But anyway, I thought this was kind of a neat and a visual representation of what's happening when we try to reduce the number of dimensions being kept, okay? And so that's kind of just like a fun little demonstration of principal components analysis, which is a way for us to reduce the dimensions, or to reduce the kind of, I guess, at its core level, reduce the amount of data or information that we have to store and think about and process. Okay, again, I'm not going to be testing you on this specific kind of stuff. You do need to know some general ideas about principal components analysis, but that's that. The other topic I wanted to kind of go over is I wanted to just kind of talk a little bit about decision trees. And so this is completely unrelated to anything else from the course, but I thought we could do it as a little bit of, say, bonus content. And I'm just using my slides from spring quarter because I did I covered kind of the same thing in spring quarter, and so it still says week 10 Wednesday, but basically we can run through how a decision tree works. And because it's a handy machine learning algorithm, and it shows up quite a bit in, say, you know, when you do random forests and things like that. You know, decision trees each kind of make up a component in a random forest. And so when we create a decision tree, basically we take our full data set, right? So the decision trees are going to be supervised learning, and it can be used for classification or regression, okay? And that you can use a decision tree to predict a value, whether it's predict the category or predict the number, okay? The thing about the decision tree, though, is that it is only able to predict one value for each terminal node. And so if your decision tree has 8 terminal nodes, okay, or 8 leaves at the end of its branches, then it is only able to predict 8 unique values, which maybe that's fine if you have a categorical variable and there's really only maybe there's only 2 categories in your categorical variable, okay? And then so you kind of have, now you've divided your thing into 8 different subgroups, and you're going to predict either red or blue for each of these different eight subgroups, and maybe that's fine. Okay, but if you are, say, predicting a numeric variable and it's a continuous variable, then you're only able to predict 8 unique values, and maybe that may or may not be a good thing. So it could be, based on these things, we're going to predict your age or something. And with this, you're only able to predict 8 unique values. Okay, maybe one of the values is we're going to predict someone is 17 and someone is 25 and someone is 35 and 45 and 55 and 65 and 75 or something like that. Okay, and you're only able to predict, say, eight unique values, and you can't predict anything in between. So either someone follows the tree and we predict their age to be 35, or maybe we predict them to be 45 or 55. It's not possible to predict someone's age to be 36 or 27 or something like that. It'll just be one of the designated kind of bins that have been created as far as the decision tree goes. Okay, and so the way the decision tree works is, we take the variables and we use those variables to kind of create a split. We just say, okay, based on this predictor variable, is the value this or this? Okay, is it greater than K, or is it less than or is it less than K? And if it's greater than K, go to the right, and if it's less than K, go to the left. Okay, or if it's a categorical variable, we'll ask, is this observation a member of group A or B versus is a member of group C or D? Okay, and if it's A or B, go to the right, and if it's C or D, go to the left. Okay, and we just kind of split and partition the data. Okay, and we keep kind of splitting or partitioning the data until we reach some kind of stopping criterion. Usually it's the number of kind of observations that fall in a certain bin is small or something. And after all of these partitions have been made, then all observations that fall in a single terminal node or leaf share a single predicted value. Okay, and again, decision trees can be used for numeric or categorical responses. We might call them regression trees or classification trees, depending on which, but in effect, they're the same. They're both decision trees. Now, how do we choose how to partition our data or where to split the data is it's what we call a greedy algorithm. Okay, a greedy algorithm. And so we try to maximize the reduction in the residual sum of squares. So if we're looking at, say, a regression tree where we're predicting a numeric outcome, okay, the tree is going to consider every possible partitioning of the data. So if you have a really big data set, training a decision tree could take a really long time because it has to consider every single partition of the data. So it's basically going to look at all of the unique values in a variable. It's going to sort them, and it's going to say, okay, what if we put one value over, separate the first value from the other 999 values, okay? And then what if we separate the top 2 values from the other 998 and the top 3 values from the other 997? And it kind of goes through and says, and it keeps going. What if we split the first 100 from the other 900, split the first 300 from the other 700 until it gets to the end, the top 990 from the bottom 10, down to the, bottom one. Okay, so it considers basically 999 different splits if you have 1,000 observations in your data. And it's going to choose the split that minimizes the residual sum of squares of the data after making the split, or another way to think of this as maximizing the reduction in the RSS. Okay, here's an example of a decision tree. This comes from 2008. This is like a long time ago. And there, at the time, this was, Barack Obama was running for president. Hillary Clinton was also running for president. And they had a Democratic primary, to try to see who would be the candidate, Democratic candidate for president. Okay, and this this decision tree was done, I don't know, halfway through the kind of primaries. So what is it? New Hampshire has their primary first, and it keeps going. And then I think so about halfway through, there were quite a few states have had their primaries, but also there were quite a few states that have not had their primaries. Okay, and so the New York Times did kind of this analysis, and they looked at all of the counties where primary election data was available, and then they tried to make predictions for the remaining states. And so looking at certain demographic information of the counties that voted, they were trying to call, who would win. And so it would ask, is a particular county more than 20% Black? And if the answer is yes, then Obama won those counties 383 to 70. So this means there were 453 counties that fit that description of being over 20% Black, and in those counties, Obama won 383 to 70. Okay, and if not, there were other kind of questions, and is the high school graduation rate higher than 78%? And the vote, if the answer was no, then Clinton won those counties, and if the high school graduation rate was higher than 87%. So this is using the same variable but creating splits at different kind of points. Okay, and so it's interesting so one thing is, it's interesting that there was first a decision tree published in kind of in the New York Times to begin with, but it also kind of speaks broadly to show that decision trees are fairly easy to understand. Okay, it's also interesting to see kind of the politics at the time, 14 years ago in 2008, I think is very different. Like, if you did not know that this was looking at Obama versus Clinton, it would be, I think, I think we'd be surprised a little bit by some of these findings, okay, compared to today's different. Okay, so how is this different from a regular regression model? Okay, so a regular regression model, like a linear regression model, you are putting in, you're looking for basically a slope coefficient. So you're saying, if we put in a number, what number do I multiply that by, and how much am I going to increase my prediction, right? So if some value goes up by 1, your prediction goes up by, the slope amount. And so it allows you to, depending on your X variable, you can have infinitely many different predicted values, right? If your X can be any value from 0 to 100, including decimal values, you can have your predicted values can be anything from well, you can have infinitely many predicted values because you can predict anything along that straight line. Whereas a regression tree, we're basically just creating, different bins based on how many nodes or how many leaves that you have. And those are the only unique, those are the values you can predict. You are not able to predict anything in between the leaves. Either you get put in this bin or you get put in that bin. And that's everybody within a bin gets treated the same. Okay, they all get the same prediction. I don't know if that answers your question, but let me just kind of give you an example of how a regression tree would kind of work if we wanted to make a prediction. Okay, and so here is a very, very simple data set. X takes on the values 1, 2, 3, 4, or 5. And the corresponding Y values are 1, 1, 3, 7, and 8. Okay. And so so you could do like linear regression, but we're not going to do linear regression. We're going to do a regression tree. Okay. So what the regression tree will do is it's going to look at every possible split. So there are 4 possible splits. We can separate the 1 from everything else, the 1, 2 from everything else. We can separate 1, 2, 3 from 4 and 5, 1, 2, 3, 4, separate that from 5. So there's 4 possible splits. Split it here, 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 and here. Okay. And then, and what we want to do is we want to look at which split minimizes the resulting RSS or maximizes the reduction in RSS. Okay. So the baseline for RSS is going to be no splits. And if we make no split, we're going to make one prediction for everybody. Okay. So if we have no split or no partition, we're going to look at all of the values in Y. And we say, okay, what is the mean of Y? 1, 1, 3, 7, and 8. Okay. This adds up to 20. 20 divided by 5 is 4. And so the mean is 4. And our RSS, our residual sum of squares with no partition, if we predict the value 4 for everyone, is going to be 44. Okay, and we get that by subtracting off the mean 4 from every value to see, what's the difference between the actual value and the predicted value, right? So actual minus predicted is 3, 3 squared is 9. Actual is 1, predicted is 4, the difference is 3, we square that, we get 9. Actual value is 3, predicted value 4, difference of 1, 1 squared is 1. I didn't put in negative signs here, but when you square them, they all become positive. The actual value here is 7. Our predicted value is 4. So difference of 3 squared is 9. And 8 and 4 has a difference of 4. And you square that to 16. You add all of these up. Your RSS is 44. Okay. Now we're going to consider every possible split. So this is the image that it looks like if we have no split. The mean is 4. These are your residuals. And when you square these residuals, you get a squared residual of 44. Okay, so the first possible partition is we're going to separate the first observation from the other 4. Okay, so I'm going to say partition A versus partition B. And so for partition A, there's only one observation. So what value do we predict? We're going to just our Y hat, we're going to predict 1. And we have no residual. And so our residual there is going to be, or squared residual there is 0. Okay. The other values are 1, 3, 7, and 8. Okay. 1, 3, 7, and 8 add up to 19. 19 divided by 4 is 4.75. So we're going to predict 4.75 for all of the other values in partition B. And so if we take the difference between each value and its prediction, and we square that, we get 3.75, and you square that and you get 14.0625. And you do this for all of the observations, and you add all of these up, including the 0, and the RSS of this, the total RSS for this split is going to be 32.75. Okay, so our image here looks like this. We have one partition that has only this observation. The other four are in this partition, and the prediction there is in the middle of all of these. And your RSS for the squared residuals for this entire split is 32.75. Okay. The next possible partition is we're going to put the first two values in one partition, and then we put the remaining three in another partition. So I have 1, 2, and then I have 3, 4, 5. Okay. Well, with these two values, their actual value is 1. The predicted value for these things is going to be 1. Okay. And so there's no residuals for these two values. Okay. Our residual is 0. So it's doing a good job predicting those values. But for the other three values, we have 3, 7, and 8. Okay. 3, 7, and 8, our prediction is the average of 3, 7, and 8, which is 6. So we're going to predict 6. And what is our residual? Okay, our residual is 3. We square that, we get 9. Residual of 1, we square that, we get 1. Residual of 2, we square that, we get 4. We add these up, we get an RSS of 14. Okay, so this possible split, potential split, gives us an RSS of 14. Okay, here we have a partition between x is 3 and x is 4. Okay, so we split, again, we're looking only at the x value, and we split based on the possible splits for x, and so we're going to split between 3 and 4. So we can say partition A is whenever x has a value less than 3.5, or partition B is whenever x has a value greater than 3.5. So what is the value that we would predict? We would predict 1.667 for which is the average of 1, 1, and 3. Okay, so 5 divided by 3 gives me 1.667. And I can say, okay, what's the difference? And we square these, and we get 0.66 squared is 0.44, et cetera, 1.778. And then over here, we have 4 and 5. The values for 4 and 5 are 7 and 8. And so our predicted values are going to be 7.5. So our residuals are 0.5, and when we square them, we get 0.25. And so when you do the RSS total residual sum of squares for this split, you get a total of 3.1667. Okay, and this is kind of what the image looks like. So if we put these three values over here, we're going to predict 1.667, and here are the residuals for this. And over here, if you have 4 and 5, we predict 7.5, and these are the residuals there. And the total RSS, 3.1667. Okay, and then we have one more possible split. Okay, and here we would put 1, 2, 3, 4. X is 1, 2, 3, or 4, and so your y values are 1, 1, 3, and 7, and your y hat would be 3 for all of these values. And then for partition B, which only has 8, your y hat would be 8, and you'd have no residual. When you take the difference, you're going to get a total RSS of 24. Okay. How do we select partitions? Do we just try every combination? Yes, you try every single combination, okay, every single possible split based on X. So you basically sort by X. You put X in order from least to greatest, and then you can consider every single possible split between unique values of X. So if you have 1,000 observations, and if every X value is unique, you would have 999 splits to do. Now, if some of your X values are duplicates, then that reduces the number of splits that you would consider. Because, if you have, if X is, if you have multiple values with the same value of X, you would consider, okay, what if I split, let's say you have a bunch of observations where X is 10. Okay, so you could do a split at, say, 9.5. And 9 and lower go into one bucket, and 10 and higher go into the other bucket. Or you could say, let's do a split at 10.5. Okay, And then all those observations at 10 go into the lower bucket, and everything at 11 or higher go in the higher bucket, or something like that. So, so yeah, you have to consider every single possible split. And so it is computationally expensive in that you have to do a lot of calculations to figure out how to do, where are you going to find what's the optimal partition. Okay. But anyway, this one results in an RSS of 24. Okay. And so we can see, oh yeah, this one predicts this one well, but doesn't do a good job for this one observation, doesn't do a great job for these observations. So we end up getting a higher RSS. So looking at all of these possible splits, okay, so we considered 4 of them. We had 5 unique values of X. So we considered 4 possible splits. The best one was this one, where we split between X is 3 and X is 4. Okay. And that's the one that minimizes the resulting RSS or maximizes the reduction RSS. We started off at 44, an RSS of 44, and splitting between 3 and 4 results in an RSS of 3.1667. And we didn't get any smaller of an RSS than that. Okay. And I can kind of duplicate these results in R. There's a bunch of different libraries out there, but here I can use rpart. Okay, rpart is a function, and so here I'll create a data frame. X takes on the values 1, 2, 3, 4, 5. Y takes on the values 1, 1, 3, 7, and 8. And I'm going to do rpart. And I'm going to say predict Y based on X. And I have to kind of, by default, I think rpart doesn't do a split if there's fewer than, like, say 10 observations in a bucket. So, but anyway, I say still make a split even though there's only 5 observations there. And what we can see is that, yeah, there's prior to it, the total deviance, residual sum of squares is 44. And if you, and the predicted value there is 4.0. Let me just pull up the same slide here. I just want to show that we get the same results. As what we found right here. Okay. So if you compare kind of the findings of this slide, okay, so we're going to do a split where X is less than 3.5 or X is greater than 3.5, greater than or equal to 3.5. Here is how many observations. We have 3 observations in the lower split versus 2 observations in the higher split. The next number, 2.667, is the total of the RSS. So if I take this number, 1.778 plus 0.44 plus 0.44, this is the total deviance for this split. And this 0.5 is the total deviance for the other split, 0.25 plus 0.25, for a total of 3.1667 if you add these 2 numbers together. The predicted value for this value, X less than 3.5, the predicted value is 1.667, which is what this is, and the predicted value for the other split, or the other half of the split, where X is greater than 3.5, your predicted value is 7.5. Okay, and that's how we read this tree. And that's what this basically says. At level 1 is the root, 5 observations, square deviance is 44, and then the results of the split. Total RSS is this. And so these results match what we did when we were kind of looking for the split manually by hand. Okay. You can ask for a little bit more information. You get this number called the complexity parameter. Okay, this first column stands for complexity parameter 0.928. And this is basically how much of the RSS did we reduce? Okay, an improvement of 0.928. So prior to the split, our RSS was 44. After we did the split, our RSS was 3.1667. Okay, so the amount of reduction, 44 minus 3.1667 is 40.83. Okay, 40.83 is 92.8%. And that's what this complexity parameter is. It's saying how much of the RSS did you reduce? 0.928, 92.8%. Okay, you can plot plot the tree. And this is not a very interesting tree, but it says, okay, this is the split. If X is less than 3.5, yes, go to the left and you get your predicted value is 1.667. And if the answer is no, go to the right. Your answer is going to be, your prediction is 7.5. And so we have two terminal nodes. Okay. If you have more, probably more variables and more terminal nodes, it would look a little bit more like a tree. Okay. You could do regression trees for larger data sets, and it just requires you to search over every possible split across every possible variable. So, for example, if you had 5 variables and 100 observations, okay, and each observation had unique values, or each variable had unique values, then you would have a total of kind of 495 partitions to consider for the first split, right? You'd have, for variable 1, there's 99 possible partitions to consider. For variable 2, there's 99 possible partitions to consider. For variable 3, there's 99 possible partitions to consider. And each of these things, you have 99 of these splits to consider, and you'd have a total of 495 splits. And so you can see that this is going to get quite computationally expensive for large data sets. It grows very quickly. And so if you have, if you're doing something like a random forest, which employs multiple decision trees, it could take your computer a long time to compute all of the different regression trees. Okay. The decision tree is what we call greedy, or basically kind of like an instant gratification thing, where it's just going to choose the one split that reduces the RSS the most in that one step. It's not going to consider like looking ahead into the future and seeing like, okay, maybe I'll take a less optimal split now so that I get better splits later. It just looks, it says right now, which is the very best split I can do, and it's going to pick that one. Okay, and that's going to be a greedy approach there. Okay, and then after you split your data, now you have basically on one side you have a smaller data set, and on another side you have a smaller data set, and you repeat the process. Okay, you kind of do it recursively in that you so let's say you had 100 observations in the beginning, and you split it, and now you have 40 and 60. Okay, now you go to that 40 data set of 40, and you do the same kind of thing. You say, okay, what's my total RSS right now? If I consider a split, how much can I reduce my RSS? And you go through that. Okay, you go to the one on the other, and then after you complete that, you go to the other side. You say, okay, here's my 60 observations. My total RSS is this right now. If I split my data here and here, how much will I reduce my RSS? And it keeps doing that recursively until you reach some kind of end. The question is, when you do add more variables, you can grow the tree and have better information, right? Additionally, how do you choose which variable to be the head of the tree? So there's no decisions. You're not choosing which variable to use. The decision tree automatically goes through, goes and considers every possible variable and every possible split. So if you have 20 variables, the decision tree is going to look at all 20 variables and it's going to consider a split, basically all partitions for that thing. And then looking across all 20 of them, it says which one reduced the RSS the most. And it's going to pick the one split that reduced the RSS the most. And that's going to be the very first split. And then it repeats it again. And it's going to consider in the next thing, it's going to consider all 20 variables again. But this time there's fewer observations because you've split your data into 2 partitions. And it's going to consider every possible partition there again. And it's going to kind of keep repeating the process. And it just does this over and over and over again. And we keep going until we reach either a maximum tree depth. You say, you know, I don't want to go have more than 5 splits or 4. I don't want my tree to go more than 4 or 5 deep, or I don't want to have, you know, fewer than 10 observations in a resulting terminal node or something like that. And so it'll just keep going. Okay. And at the end, it assigns a single kind of predicted value to each bucket. You can, once you kind of create a split, you could prune the tree, right? And so you can, so if you, question says, I see, wait, hold on, what's going on here? So you can tell your model to only have, say, the top 3 best variables out of 20. You don't, so basically it's going to, it doesn't know prior to creating a decision tree or running a random forest or something like that. It doesn't know which variables are best. Okay. It's just going to look at all of the variables, do all of the splits. Okay. And it's going to say, well, this one resulted in the biggest RSS reduction. And that's what it's going to choose. And then once it does that, it just repeats the process and it says, okay, let's look at all the variables again. And at the end, it can say, hey, these are the variables I split on the most, I used to kind of make my splits most often. All right. And, or, you know, with a random forest, you can say, well, random forest is something different, but, you know, when you do the decision tree, you can kind of try to mix it up a little bit by, you know, doing some bootstrap resamples, you know, we call this bagging. And you can say, all right, well, what if I mix it up a little bit? Are we still going to pick the same variables? And the answer could be, yeah, you know, anytime you use this variable, you get the biggest reduction in RSS. Okay. And that's why we think this is the best variable. But prior to kind of considering all of the possible splits, you know, the computer has no idea which variable is the best or which one's going to result in the biggest reduction in RSS. So, so yeah, the algorithm just kind of looks at all of them, and whichever one results in the biggest reduction in RSS, it's gonna use that one. Okay. Here I'm gonna overfit the model intentionally. Okay. And I'm going to just say, keep making splits. All right. And we're going to say, consider split even if you only have 2 observations, and the minimum complexity parameter, so the minimum reduction in RSS is going to be 1%. And if we do this, we end up getting a tree that creates 4 terminal nodes. Okay. And basically we get a terminal node for each unique value of y, right? So I had, the values were 1, 1, 3, 7, and 8. And I get a split at, my first split's at 3.5. Okay, and then after I split 3.5, I make a split at 2.5. Okay, and at 2.5, values less than 2.5, we predict 1. Values greater than 2.5, but less than 3.5, we predict 3. Okay, and now we have no no residuals here. Okay, similarly, if I split at 3.5, I'm going to predict 7.5, but then I can further split that, and I can split at 4.5. Okay, and values greater than 3.5 but less than 4.5, we predict to be 7. Values greater than 4.5, we predict to be 8, and that's what this is saying. And so we get 4 terminal nodes equivalent to the number of unique Y values, and this is overfitting our data. And so we can prune the tree. Okay, so we're just kind of going with the tree analogies and the terminology here. And we're going to say, okay, let's find kind of the weakest link or the weakest branch. And so, all right, which one should we remove? Should we remove the split at 4.5, or should we remove the split at 2.5? Which one is less important? Okay, so here we went from the split at 3.5 goes from an RSS of 2.66 down to an RSS of basically a total of 0, and the split at 4.5 goes from an RSS of 0.5 to 0. So the one at 4.5 reduces the RSS less, right? So one, we went from 2.66 down to 0. Okay, so a reduction of 2.66, which is around 6%, that's going to be the complexity parameter. Whereas the RSS at 4.5, the total RSS prior to it was 0.5, and now it's 0. So we've reduced the RSS by 0.5. 0.5 is 0.5 divided by 44 is around 1%, a little over 1%. Okay, and so this is going to be kind of the value, the complexity parameter associated with this split around 0.0114. So that would be kind of the weakest link. All right, so if we look at these complexity parameter numbers, the first one was 0.928, the next one was 0.06. Okay, and again, that comes from 2.66 divided by 44. And then this last one was 0.5 divided by 44, and we get 0.0113. Okay, so this is kind of the complexity parameter. This 0.01 is, I specified, and I said that's kind of the bottom floor if we're going to have any of this, right? So if I were to prune the tree and I say, all right, we need to have a minimum complexity parameter of at least, say, 2%, then it would get rid of this final split at the end. Okay, so if I say prune the tree, get rid of any kind of split that has a complexity parameter less than 2%, then it gets rid of that split. Okay, so now it does a split at 3.5 and a split at 2.5, but it doesn't do the split at 4.5. Okay, or you could say I want a minimum complexity parameter of, say, 10%, 0.1. Okay, and then it gets rid of the split right here, because this one had a complexity parameter of around 6%. Okay, so if you say the minimum complexity parameter, the minimum reduction in RSS needs to be at least a 10% reduction, then it gets rid of the other splits. Okay, so the other splits removed, we're left with a simpler tree. All right, how do we choose the complexity parameter? Okay, you can do kind of cross-validation, and RPart can do this. And so here I have just an example from a slightly more complicated data set. This is like an old data set on cars, and we're trying to predict the value of the car, the price of the car, based on kind of its gas mileage and what type of vehicle it is and what country of origin it's from. And I think this data set's from like the 70s or the 80s. So I don't know It's probably outdated and not very good anymore, but we can just kind of, I can run, create a regression tree based on this, and it creates all of these splits. And I can say, you know what, let's try to figure out what an appropriate complexity parameter is to use, okay? And so the guideline says a good choice of complexity parameter for pruning is often the leftmost value for which the mean lies below the horizontal line, okay? So what is this horizontal line, okay? The horizontal line is basically, you look at the minimum cross-validation error, all right? So so this reflects more and more complicated trees, right? So the size of the tree, as we go to the right, the tree gets more and more complicated. And what we're seeing is that as the trees get more complicated, the amount of error that we have in our predictions get lower and lower, okay? And then actually at 6 and 7, it actually goes up a tiny bit. And so the lowest error that we achieved was with a complexity parameter of 0.026, the tree size 5. And then there is a standard error, right? There's some standard deviation based on the error. So sometimes you make a tree of depth 5 and it has a certain amount of error, but then when you do cross-validation, you know, like tenfold cross-validation or something like that, and you do another kind of train test split or validation split, you get a different amount of error. So this is kind of keeping track of the amounts of error, prediction error that we're getting, and it says, okay, well, there's a standard deviation for the amount of prediction error. And so this horizontal line is drawn at one standard deviation above the minimum. Okay, so the minimum cross-validation error happened at tree size tree 5 or complexity parameter 0.026. One standard deviation above is, I don't know, around this number of 0.7. And what is the, can we have a smaller tree where kind of the mean cross-validation error is still less than that, okay? And so here with a tree of size 4, which is less complicated, it's actually the amount of error goes up. So we're going to say, okay, this is not any good. And so we would stick with the 5. Now it is subject to randomness. So there is a minimum. Okay, so actually, I think because of randomness, we got some slightly different results, and I ended up picking 0.074. Yeah, okay, so this one, okay, that's interesting. When I reran it, both of these times, the 4 is higher than the line, okay? So the 5 was the lowest at 0.026. When I ran it again, I got different results again, but again, the lowest happened at 5 at 0.026, and this one still ended up higher. So we would choose 0.026. Okay, so I think at one of my random runs, and it changed when I knitted this here, the complexity parameter for 4 ended up below the line, not 4, the mean cross-validation error for size of tree 4, 0.074, ended up below the line, and I would have kept that. But in this case, it's above the line. And in this case, it's also above the line. So I'm not quite sure what I did. Set seed 10. It's interesting. Okay. Something different happened here. Okay. But anyway, all to say, there you are subject to some of the random forces that happen when you fit a model. Okay, and so that's something to always be kind of aware of, is randomness, especially when you're doing something like random forest or cross-validation. There's a random component, and your results may end up being different from one run to another. So if you have the time and the computational power to afford it, you can you should run it multiple times and see if your results are consistent. And if they are consistent, then that's a good sign. But if you run it multiple times and your results end up quite different, then you're in a situation of high variance, right? Your bias might be low, but you're in a situation of high variance where your models are kind of changing rapidly from one model to another based on just some kind of random forces. And that's an undesirable feature. So you'd like a model that remains fairly consistent, exhibiting low variance, but you don't want it to happen so much that to be so consistent that it's basically not saying anything interesting either, where you end up kind of in this high bias, uninteresting results there. Anyway, this is just a little bit on decision trees. I didn't include slides for random forest, but I'll just kind of talk a little bit about random forest. The way random forest works is you're going to fit multiple decision trees to the same data set. But what you do with random forest is, because if you just fit the same decision tree, you say, hey, fit the same decision tree, or fit a decision tree to the same data set, all these decision trees would end up looking the same. So with a random forest is you kind of, you disable the decision tree a little bit, and you say, you know what, you're only allowed to use these variables. Okay, so maybe your full data set has 50 variables to choose from. When you do a random forest, you say, I want you to make a decision tree, but you're only allowed to use these 5 variables rather than the full 50. And so looking at those 5 variables, the decision tree says, okay, the best variable is variable 2, and the next best variable is variable 3, or something like that. Okay, and then a different decision tree gets a different random 5 variables, and maybe they get random variables 30, 31, 32, or something like that. And it says, okay, among these 5 variables that we've been given, the best variable to use will be 32, variable 32, or something like that. Okay, and so the random forest forces your decision trees to end up to be different from one another by restricting which variables it can use. And you might say, well, why would we want to do that, right? Why wouldn't we just use the best variable all the time? Okay, well, if you have no restrictions and you say use the best variable every single time, then pretty much all of your decision trees will look identical to each other. You can kind of say, you know, we'll do some bootstrap resampling, we'll do some bagging to kind of introduce a little bit of variation, but pretty much all of your trees will end up looking exactly the same. By limiting each of those decision trees to using only a certain number of variables, it will force all of these decision trees to be a little bit different. Okay, and then at the end, you just take the average of your different trees. So some trees will perform better than others. And at the end, the model is going to take the average of all of the different decision trees that were created. And that ends up performing better than just relying on one tree alone, or relying on a bunch of trees that are identical. By having kind of a diversity of trees, we end up getting better performance by kind of taking the average of all of these different trees. And that's what happens there. Okay, this was just, I guess, a lecture of, say, bonus content, not anything that I will be testing you on. I hope the description that I provided regarding the final exam is okay and adequate. I know there's some confusion regarding the emails and whatnot, and I kind of checked with the stats department and the leadership there, and basically our classroom is not on the list of having no AC. So our classroom will have AC. the office buildings and some of the other, like for holding office hours and stuff, those are without AC. But Young Hall still has air conditioning, so we will still have an in-person final on Thursday morning. So the final exam will still be Thursday morning, 9 a.m. In person at Young Hall. I'll send out a seating chart. I'll make sure I get it right this time. And other than that, good luck as you study, and we will see you on Thursday for the final. So thank you.
Thank you.
And have a great rest of your day. Good luck, and we'll see you for the final.